Okay, let's get started. This is our third day plenary talk. It is my great honor to introduce Professor Susan Murphy. And Susan is Malignant Professor of Statistics and Computer Science from Harvard University. And her research interests focus on improving sequential, individualized decision-making in digital health. She developed a micro-randomized trial for use in constructing digital health interventions. And this trial design is in use across a broad range of health-related areas. Her lab works on online learning algorithm for developing personalized digital health intervention. Professor Murphy is also a member of the National Academy of Science and the National Academy of Medicine, both of the US National Academies. In 2013, she was also awarded MacArthur Genius Fellowship for her work on experiment design to inform sequential decision-making. She's a fellow of a college on problems in drug dependence, past president of IMS, past president of Bernoulli Society, and also former editor of the Annal of Statistics. And from my personal side, Susan was my professor when I was a graduate student at Penn State. Actually, in fact, I was her TA once. So welcome, Susan. It is a great honor.
It's a pleasure to be here with everyone. My whole life I've been trying really hard to bring both my applied side and more of a theoretical side together. And this has been an enormous struggle for me. I think many of you will understand what I mean. It's very hard to have to do something that actually has impact and at the same time has a theory side to it. And this is one of the first times that I felt like I really have begun to make some progress in that direction. And that's the reason why I wanted to talk to you about this. So this work is motivated by two studies that are about to go into the field. Oralytics will be in February, and then the one for kids that are smoking too much pot will be in the summer. But we're going to talk about oralytics today. Right, so thank you for collaborators. I have much of the work today is by Kelly Zhang. She's a PhD student in CS, as well as Anna, a behavioral science colleague in the middle, Billy Nahum Shani, and Vivek, who's a dental surgeon, and then Lucas Janssen, who's a statistician like me. And there's a large software engineering team here as well, involved as well. Okay, so I'm going to talk to you about oralytics, the study that got things going. So the task here is to develop an autonomous oral health coaching intervention for individuals at high risk of dental disease. This study, there they are. This study will run, it's running in Southern California, and they are individuals that are struggling to improve their health. You see, it's a 10-week trial, only 10 weeks, very short trial. And it has it will have around 75 users. There'll be multiple trials in a series. This is the first of several trials that are funded towards working on this application. And the trial is going to involve what we call micro-randomization. And in particular, these randomization probabilities are determined by a variant, will be determined by a variant of a reinforcement learning algorithm. And this is where the challenges come and the excitement and the challenges. So in oralytics, there's 2 decision times per day, corresponding to the usual time you brush. That person brushes. There's a large amount of sensor data coming in from the Bluetooth enabled toothbrush, as well as the app on the individual's phone. I just list some of the important state features. The action is here, the action we're going to act, the RL algorithm will act as if the action is only binary. In fact, there's 4 actions at each time, but we'll focus on send a engagement message versus not. And an example of engagement message is on the far left. They're all related to if you provide a present to someone, will they then reciprocate and do something you're trying to help them to do? It's the idea. At the very bottom, I list the reward. This is the algorithm's reward. It's a measure of the efficiency of the individual's toothbrushing, and this comes from the sensors. It's constructed based on the sensors on the phone, from the app, the toothbrush. So here I just give you a little schematic of the trial. Again, here's the morning. There's actually 4 different actions written here. And here's the evening. There's 4 actions there. And it just continues on through time. And the probability of either getting some sort of nothing versus something will be determined by the algorithm. There's only 70 days. Only 2 decision times per day. Right away, if you know anything about reinforcement learning, you should be really worried. Okay, so as I mentioned at the very beginning, there's a whole series of studies that are planned, and this is just the first. This is the first in that series. And so in these types of settings, you have both within study learning and between study learning. And it's absolutely critical to be able to do both. I'll talk a little bit about that chart now. So within study learning, this is all about personalization. Can you learn on the individuals in front of you in order to better deliver messages versus not? Usually one uses bandit reinforcement learning algorithms for this. That would be the natural thing to do. Then between studies learning, that learning involves other types of questions, predominantly causal inference type questions. And usually in this setting, in the particular setting of oralytics and in general in the digital intervention space, there's tons of different interventions on the app. And here you might be interested in what's the effect of these messages on other ways of engaging with the app, like monitoring your behavior, for example. So that outcome is not necessarily related directly to the reward for the algorithm, but it's an important outcome that people would be interested in. And you're often interested in, does this impact, differential impact between the messages? Does it differ by the current user state? So you want to do both within study learning and you want to do between study learning. Okay, so let's go to within study learning. So here, the brushing efficiency score, that is the reward for the algorithm. It's very noisy. This is typical in these settings where you're experimenting as someone goes about their daily life. The outcomes do tend to be quite noisy. There's only a few decision points per person. 70-day study, 2 times a day, 140 decision points. You really have to be worried about the algorithm that's running during the study. Is it going to learn anything at all? And of course, there's a whole variety of things that we attempt to do to manage this slow learning, to speed the learning up. In this setting, for example, with oralytics and in general, we tend to use Bayesian algorithms, RL algorithms, and we use informative priors. No non-informative priors for me, only informative priors. And the priors are built on prior data from a similar population using similar sensors. But here, how are we going to think about it here? Only 140 time points per person. We're going to have that informative prior, but we still have a problem. And what we want to do, we've been wanting to do for some time, is we've been wanting to use an algorithm that pools data across users as they go through the study. And in fact, this is typical when you develop these types of interventions. You have to first develop a simulation test bed, and you have multiple variants of that test bed, then you have multiple variants of the RL algorithm, and you try them all out all possible combinations. And pretty much all of our variants do better if we pool completely across users. And these are very heterogeneous users in general, okay? It's just that you only have 140 decision times per user. So that's the reason why it's worth it to pool across users. So we really want to do this, and we've been wanting to do this for some time. I mean, this is not new that we want to pool, have the algorithm, the online algorithm pool across the users during the study. And we never could. And the problem is we didn't have a way to analyze the data afterwards. And these types of trials, they involve a large group of stakeholders, and each individual has a whole variety of analyses they want to run after the study's over. And you can't run an online algorithm which all of a sudden precludes all the stakeholders from conducting their own analysis. You just can't. That's just not how this game is played. The study itself is everything costs too much. So the work I'm going to talk about today is trying to meet that challenge. One wants to be able to run a variety of different analyses after the study's over, a lot of time, often having to do with causal inference. And you have to be able to enable that, even though the algorithm, the RL algorithm pooled. So that gets us to this whole issue of dependence and some, and there's actually two issues I'll talk about both briefly. Okay, so let's think about this study. So these are, all of these individuals will be recruited into this study. As I said earlier, they're coming up from Southern California, and they don't know each other. They're not going to meet, there's not going to be any meetings between individuals. So they come in at the very first time point. You can see the state, this is the context of the individual. The action here, send a engagement suggestion versus not. This probably, well, in fact, here it's going to be randomized the first time with probability 1/2, and then we'll see the brushing efficiency score. The algorithm will input the brushing efficiency score. These individuals could be, you can view them as IID, their data coming in as IID. Then what will happen is an analysis, the software will run an analysis, and it'll produce a policy. And you see I wrote a little formula for the policy at the very bottom of the slide. And this policy will depend on a set of parameters. If you're using Bayesian inference, these parameters there might be posterior means, posterior variances. It just depends on the algorithm that one is running. But in general, there's a set of parameters that index the policy, and the data that you use to build this policy is just the individuals from their first time point. So you build that policy. Now at the second time point, you look at the first user state. The algorithm looks at the first user state. It inputs that into the policy, and then you get a probability for the action, send a suggestion versus not, at the second time. And then you do that for every single individual. So the algorithm does this online for every single individual. Then you take that data. Now you have data from every person, 2 time points. You update, the algorithm updates the probabilities. Here they're written again. Again, you have this indexed by some set of parameters, and so on. So what have you done? What you've done is your algorithm has you've input independent users, independent data, and you've produced dependent users. That's what you've done. And they're dependent because, for example, if I'm in the study and Anne's in the study, then how Anne responds to the messages determines what kind of message I get next. So this dependence is very odd. It's due to the fact that this policy is being learned, and you're sharing data to learn the policy, which then goes and is used to choose the next set of actions for everyone. But how do we do after study or between study analyses in most clinical trials? in most clinical trials, you view your data, the data stream, one per individual, you view it as longitudinal data. So what do I mean by longitudinal data? This is the ith user. The ith user has a series of tuples at every decision time. Capital T is 140 in this study. So you have a set of observations. Your state for the algorithm is a subset of those observations. You have the action at each decision time, and then you have a set of outcomes. The reward for the algorithm, you can view it as a subset of the outcomes. And you have that for each of n users. So when we say the word longitudinal data analysis, what are we thinking in our mind? What we're thinking is we're going to permit there to be an arbitrary dependence within an individual across time. You may model it. It depends on whether or not it's a primary analysis, a secondary analysis, or some other type of statistical analysis. But in general, you want to allow the dependence within an individual to be very general in terms of those observations, the actions, rewards. But the way in which in longitudinal data analysis, we accumulate information, we assess measures of confidence, produce confidence intervals, is we tend to assume the users, in general, the units, here users, are IID, independent in particular. And we also make other assumptions which are, they're not as overt. And that is, for example, that the average action in any particular state concentrates. That is, as the sample size increases in the number of users increases, it should converge to some point, like a number between 0 and 1, because this is a fraction. This is just a fraction of the time at time t that a suggestion was sent. It shouldn't converge to a p-value, for example. Well, it turns out RL algorithms, that doesn't happen in general. So the thing is, in an RL algorithm, it generally results in sampling probabilities that may not concentrate. They don't converge. If you take an average of the probabilities across individuals, it's not going to converge to some number between 0 and 1. It's almost like you're getting a draw from a uniform distribution in some settings. And your trajectories, of course, are not independent because we're pooling across individuals. So the adaptive sampling that's performed by the reinforcement learning algorithm or the bandit algorithm, it produces data that violates sort of the standard assumptions we use when we have longitudinal data. That is, users are independent and that certain averages converge, they concentrate, they converge to some constant. Here's a little graph at the very bottom of the screen. This is a simulation in which all we wanted to do was estimate a treatment effect. So the comparison of the outcome, if treated minus the mean of the outcome, if treated minus the mean of the outcome, if not treated. So it's just a difference of two sample means. And the algorithm was a Thompson sampling, a bandit algorithm. And the red line here is a normal distribution. And then you can see the histogram of the actual distribution of the difference between the sample means. It's definitely not normal. And you end up with, like, if you aimed for a 95% confidence interval, you get 10% error rate. Okay, I want to say this area of adaptive sampling, this has become quite hot currently, and it's mainly not due to its use in this particular domain. It's mainly due to its use in advertising and in the use on the internet. So advertising on your Facebook page, advertising on your Google page, and so on. And in that setting, there's been a good bit of work about how we should analyze adaptively sampled data. And in general, the way in which the work at this point in time, what they do is they make whatever assumptions were used to construct the RL algorithm or the bandit algorithm are then carried forward. And now whatever data analyses you're going to use are so you make those same assumptions. Okay, so all of the approaches for managing this data from your users makes the same assumptions as the algorithm that was run online. That doesn't make sense if you're in a health field. You don't want the assumptions made by the algorithm to necessarily have to hold in order to conduct a variety of analyses. Okay, so how are we going to deal with this? Well, the first thing we're going to do is, because we have to learn both within a study, i.e. personalize, as well as learn between studies, we're going to abandon the goal of regret minimization. So if you're going after regret minimization, that's exactly when you get these non-concentrating probabilities. In particular, this is because one reason is because the analyses are forming non-smooth operations on the data, like they're taking maximization, repeatedly maximizing. So we'll use a soft max instead of a hard max, and we'll also ensure there's always some level of exploration. And indeed, this is exactly what's done when you're in a setting where you want to have reinforcement learning in many non-stationary settings. So in more complex settings, you get RL algorithms that have this flavor. In general, in our setting, we'll also have this. I'll be a little bit more precise, but many algorithms, it's very easy to make them satisfy this, but not UCB. Okay, if you love UCB, forget it. It will not work unless you change it a good bit. In this setting, the great thing is now all of a sudden one can approximate, for example, a treatment effect that's estimated after the study's over by the distribution of that treatment effect by a Gaussian distribution. So it becomes like, it's almost like you're in classical statistics once again, because you give up regret minimization within a study. And now you're balancing within study learning and between study learning. The only issue is, because we're pooling across individuals, is you still have more variance than you would think. And this makes perfect sense if you're a classical statistician. You know that when your data is dependent, you don't have if you have N users, you don't have N independent sources of information. So this makes good sense that somehow you're going to have to manage the variance. Turns out that ends up being a little problematic in itself, and that's most of what I'm going to talk about. What I'll talk about with you. So again, the first assumption is to facilitate concentration, and what I mean by concentration is I mean those sampling probabilities, they converge. So as N, the number of users goes to infinity. So these are the sampling probabilities from the RL algorithm. It depends on the algorithm. These tend to be like posterior means, different types of regression estimators. They're re-estimated at each time, and they should converge to some, they should have a limit. And that's what we mean by concentration here. And again, I already said this, you're going to be in a setting where you can use standard normal asymptotics, but you have to deal with the dependence between the users. Okay, so that's what I'm going to talk about now. And this is the point that really stymied us for quite some time. Okay, so right now I'm going to teach you classical statistics, because I know everybody's doing deep learning now, so we've forgotten classical statistics. I can't remember when this is from, these ideas. I think they're from the 1940s or something. I don't know. It's like eons ago. So suppose I want to conduct inference about a treatment effect, theta star, and I have ID data trajectories, so standard setting, and I have some estimating function. The estimating function could be I could be doing maximum likelihood, and my estimating function is the derivative of the log likelihood. So the setup is the parameter I care about, it solves the expectation of my estimating function. This expectation is over this data, the DI, IID data. So theta star solves this, and I estimate it using a Z estimator. And so theta hat solves the empirical version. So this is, like I said, I think this is 1940s. I'm not sure, Peter. It must be 1940. It must be. Anyway, it's a long time ago. Here's a good example where I just use least squares and I just take the first derivative in a least squares equation. In a sense, what I'm doing is these weights, the theta 0 and the theta 1, they're projections. I'm projecting the conditional mean of this outcome, this reward, on the space spanned by the states and the action time, the action indicator time, the states. So the estimators that I'm interested in are the projections, the projection weights. They satisfy the population average, and I estimate it just by using an empirical average. So it's just classical statistics. So, okay, so let's get back to our problem. So it's clear that we're going to have to somehow propagate the variance that occurs due to the fact that we used a learning algorithm online during that study. And that has variance associated with it. And that variance then gets propagated into the variance of whatever, say, our treatment effect estimator. So again, remember these betas, this is the policy that's being learned during the study. At each time point, you have a vector like posterior means, for example, or regression weights. And we want to mathematize how our estimator of the treatment effect, this is the estimator we're going to conduct this, we're going to estimate this theta star after the study's over, between studies in our case. We want to understand the variance of theta hat. And we know it's got to be a function of how these policies were built. How do we do this in statistics? So again, I don't know when this is. Maybe I'm getting into the 80s, 1980s, I'm not sure. So what we do in classical statistics is we try to understand the derivative of the estimator of the treatment effect as a function of the estimators of the policy parameters. And of course, that makes sense to do that because as these estimators vary, the derivative propagates that variance into the variance of the estimator of the treatment effect. So perturbations here propagate into perturbations into the estimator of the treatment effect. So it makes perfect sense you want to do that. It doesn't seem like this is really special or anything hard to do. Okay, so how do you think about this in classical statistics? Again, we're moving through time. So I know my estimator of the treatment effect is some implicit function of a whole bunch of other estimators. So in the classical setting, what happens is our Z estimation, our estimating function here is with that's psi. This is a Z estimator of theta. It involves those other functions that you had to estimate. In our case, these are the estimators from the policy that's used to collect the data. And then here you solve this, and then you get theta hat. And what do we do classically? If we're a theoretician and we're just trying to get asymptotic statistics, classical asymptotic statistics, is we differentiate both sides of this equation with respect to the policy estimators, that is the beta hats. So we get 0 on this side. We get a derivative of theta with respect to those policy parameters. And then we get a derivative of psi with respect to the policy parameters. And you solve for the derivative of theta with respect to the policy estimators, and you're good to go. This is all, and then you use classical asymptotic statistics to propagate, to produce a variance estimator for theta hat. No problem. That's exactly what I just said here. Again, I just want to remind you, you differentiate both sides of this. And that's how you get your, how you understand the derivative of your estimator of the treatment effect as a function of the parameters in the policy. Okay, I got a new microphone. But this doesn't work with us. This is a disaster. This doesn't work. That's why I got a new microphone. And actually, I've been trying to think about this from some years because I'm under a lot of pressure to pull and have an algorithm that pulls. It just doesn't work. What happens to us in our setting? In our setting, these estimators that are used in the policies, this one is used in the policy at time t, decision point t, it is only used to decide what data you get to observe. It's not in the estimating function. It's determining what data you have. That is, the action, the binary action, send a suggestion versus not, is selected with this probability at time t. Our estimating function, it doesn't have a beta in it. It doesn't have any betas in it. It's a disaster. How do I differentiate both sides of this equation with respect to the beta hats when there's none? The thing is, they're all implicitly in the data. Okay, so this was quite the conundrum for some time. I figure Emmanuel already knows how to solve this. But I was flummoxed. I didn't know what should we do. And then one begins to think about what does it mean, to take a derivative. And with a derivative, what you do is you want to take the derivative from many different directions as you go through theta hat. So derivatives are often, they're thought of as local. They're local to that value of, and in our case, we want a derivative at the point beta hat of theta hat at the point of the beta hats. So somehow we have to get a local, we don't want just a point estimator of theta hat. We want a theta hat that's local for all the betas that are close to the policy parameters. That's what we want. And how do you do this? Okay, so here's the idea. Oh, do I get another one? Okay, I'll just keep this one. How do you do this? What we did was, this is just a theoretical tool. I would love to see if anybody's seen weights used simply to do math, not for estimation, simple math. It's to allow us to do differentiation. So here's our, we recognize that local to these policy parameters, I can think of my estimating function being of this form. So here's the one I had before, it's the usual, and now I have these sample weights. This is a radon-nicotine derivative. So the denominator is how the data was collected. The numerator is just arbitrarily indexed by these index variables, the betas. And now I can think of a theta that solves this equation. And if theta hat solves this equation, it's a function of these numerators. So now I can differentiate both sides with respect to all the beta, the indices. So I differentiate both sides. I get a contribution of with respect to the betas from these weights, and I get the derivative of the parameter I care about, the theta with respect to these betas. And that's all local. Of course, in real life, none of this happens, because in real life, you put in your estimators of the policy parameters, and this whole weight just becomes one. So in real life, this is not there. This is only fictitious in our mind as we get derivatives, and it works. So now what we do is we differentiate both sides. We solve for the derivative theta with respect to the betas, and now you know how to propagate. There's some more things one has to do in order to work in this problem, because you still have dependence between your people, but now you know how to propagate the variability. And there's no weighting in the actual data analysis. This use of importance weights or radon-nicotine derivatives or inverse probability weighting, it's completely just to propagate uncertainty in the math. That's all it is. So it has a theorem, of course, there's always a theorem. And in this theorem, here's the theorem. So we can think of theta hat again as an estimator of your treatment effect that you estimate between studies, and you get the usual asymptotic relationship because this is classical statistics. And if you're familiar with this type of longitudinal data analysis, the variance covariance, the limiting variance covariance matrix always has this sandwich form, this is classic with Z estimators. The outside part is exactly what one would think, and the inside part is a little different. The first term in the inside part is, again, it's what one normally sees in longitudinal data analysis. And then there's a second term. This function f, this is a linear function of these derivatives. If I tried to write it out, I'd go across off the slide. So just be aware that f is linear in this derivative. This is the only part that's different, and this is the part that's due to the use of the adaptive sampling, the adaptive data collection. It's really interesting, and if you're a classical statistician, I don't know how many, I doubt very many people do survey sampling here, but there's a close connection to survey sampling as well here. And I'll just mention that briefly. So let's look at this derivative. So if the target parameter, i.e. the treatment effect, is independent, is unrelated, can be defined independently of how the data is collected. You're not looking for projections or anything like that. You're not doing any kind of marginal analysis. Then this derivative will be 0. And in fact, this term is not there. And you can act as if your data, your user's data, the trajectories are completely independent. This happens, like I said, in survey sampling. In survey sampling, often you'll have stratified samples, clustered samples, and people will want to use sample weights. And however, many econometricians who believe their models are correct don't use the sample weights. They don't need to use the sample weights because they have a similar situation where the parameter they're estimating does not depend on how the data was collected. It's very interesting. So it's exact analog to classical survey sampling. Okay, so I'm just going to give you a little simulation. I just want to drive this point home, this point about this extra term is used only if you're estimating projections or you're estimating parameters in a marginal analysis. So here, this is the little simulation. The real reward depends on the ground truth generating model depends on all the prior actions and the prior reward. The error terms, think of a linear model. The error terms are all correlated within a person across time. And the effects of these actions are decaying, exponentially decaying as time goes on. This is the ground truth model, very, very simple model. Our simple RL algorithm for this little simple explanation is just a linear regression on the binary treatment indicator action and the state, which is just the prior reward. So it's misspecified, but that's fine. And our action, and the way we're going to select our actions is it's called Boltzmann exploration. You calculate this XBit of the treatment effect, and then we're going to clip it below by 0.1 and 0.9. That's to ensure there's always exploration throughout for all time points T. Now we're going to do our between study analysis. Again, it's very simple analysis. We're going to regress our reward on the treatment indicator state and then the product of the treatment indicator and the state. And the state is just the prior reward. This is a marginal model. It's got to be marginal because on that 2 slides ago, I told you that the reward depends on the exponentially decaying actions in the past. So this is a setting where the weights on the regression weights are going to depend on how the data was collected because they're marginal, they're projections. So we're looking at 95% confidence intervals. The usual sandwich estimator that's used throughout in longitudinal data analysis, it's just, it dies. It dies in this setting because it's just not accommodating the fact that you have this dependency, but our estimator does much better. We still need to do a small sample correction, and I expect this will get better, but I want to show you that. Now here in the second case, now you believe in your analysis after the study's over that your model is correct. Okay, that's these two columns. Your model is correct. You use the right model. You're not doing causal inference. You're not doing marginal analyses. You're probably doing some sort of mechanistic modeling and you believe it's correct. And you don't need that adjustment at all. It's exactly what one would think. Okay, so this is my last slide. Where are we right now? So as you can imagine, our team, we're going to go in February. Our team's under a lot of pressure. We have there's a biostat team working in this whole group. We have to provide the R package. In reality, people are recruited to these studies incrementally. This causes all kinds of interesting complications, more applied complications. And we have to do the small sample correction. We have to get all of that done. We are going to be using a variant of Thompson sampling in the final algorithm. And then we'll deploy the algorithm starting in February. Thank you.
Now we open floor for the questions. If anyone want to ask questions, just move up front. We try to make a better recording. Yeah, Ali, could you come?
Thank you. Susan, so I think here T was fixed, the length of the experiment was fixed, right? What happens when T grows?
These problems are non-stationary problems. So unless you're willing to make strong mechanistic assumptions, say, for example, different types of ergodicity assumptions and so on. So he asked me, what happens if you let T get large? And that's a natural thing to do. Okay, don't get me wrong, it's very natural. But these, they are non-stationary problems. And the reason is we don't sense the entire state of the individual. And also the domain science here is, this is the behavioral sciences, health sciences. That's kind of, that's on the frontier. They don't really, good mechanistic models are not available. So as a result, you see apparent non-stationarity. So this idea that you're going to accumulate information as time goes on. Of course, in secondary analyses after the study's over, it's fine to to try some model like a different types of time series models and so on. That's all fine, but you can't have everything incumbent on that. The validity of your the variety of analyses cannot be incumbent on stationarity.
Thank you.
Yeah.
Any other questions? Also, okay.
Thank you. You mentioned patient approaches. What kind of patient approaches are suitable here? To my mind, empirical based, using data adaptive, but what kind of base approaches would be best? Patient. Base. Patient.
Patient.
But B, I'm sorry. B-A-Y-E-S.
Approaches for the patient. For the patient.
Base. Yeah.
Oh, Bayesian. I'm so sorry.
Language.
Thank you so much. We pretty much stick with some variant. We're very concerned about delayed effects in this setting. So you don't really want to do a vanilla Thompson sampling algorithm, which, by the way, was invented by the biostatisticians in the last century. I just want everyone to know that. Everyone in today's world is running around acting as if it's something, totally hot. The biostatisticians invented that in the last century, just by the way. Anyway, but so we always have to, if you think of Bellman's equation, in a bandit algorithm, you only target the immediate reward. In a full RL, according to Bellman's equation, you have to also, it's the present reward plus some prediction of future rewards. And we always have to have some adjustment to try and anticipate future rewards. Often it's built on prior data. And the Bayesian part comes in so it's always approximate Bayesian. We can't use Monte Carlo Markov chain. This is online. These algorithms have to be fully autonomous. Actually, this is a whole area. This is a big challenge to you guys, all statisticians. This is a disaster. I mean, we have to be using we have to use Bayesian algorithms in this setting. We need to use informative priors, yet the Bayesian community is not giving us autonomous algorithms. I mean, I just can't tell you what a disaster this is. I just want to make that pitch. So we're having to do all kinds of approximations that are stable and autonomous in order to run, so that we get something akin to a posterior distribution, or something like a bootstrap approximation to a posterior distribution. Yeah.
Okay, thanks.
Thank you.
Surely a long question for research. Thanks.
Any other questions?
Thank you for the great talk. I have a question about setup. I will combine this. My question is that the action and the reward we observe at time point t depend on the policy we learned pi hat 1 at 10.1. And the policy pi hat 1 depends on all the observations we have at 10.1. So my question is that in this setting, all the reward and action at time point t is dependent on all the observations at time point 1. Then how the trajectories of each individual be independent?
They're not.
But in the setting, in the slides, you said that DI are IID.
Oh, no, what happens is the polling, well, it's not a poll. The individuals come in and you can think of their data as starting out as IID, but because of the way the actions are being sampled, you end up with dependent individuals. Of course, this dependence has a very special form, right? It's not arbitrary dependence because people are communicating, users are communicating with each other. It's dependence through the policy, because the policy is being learned by pooling all the data from all the individuals.
So actually, it's the observations are IID rather than all the trajectories IID.
The trajectories are not IID.
That
No.
makes sense. Thank
No,
you
they're
very
not ID. You could actually, if you're a causal inference kind of person, what you should think is the potential outcome trajectories are IID. But the way in which you sample parts of those potential outcome trajectories produces observed trajectories which are dependent.
Okay, thank you. Another question that may I ask, currently, how do you choose the policy pi hat?
Yeah, so in this toy example, we used we just used regression and Boltzmann exploration. However, in general, what in our studies, we're focusing primarily on Bayesian approaches, where you use the policy is it's the posterior probability that one action is better than the other actions. So the probability that action A is selected in a particular state is the posterior probability that action A is better than all the other actions in that particular state.
May I ask what's the difference between your current method and Thompson sampling?
What's the current method?
The method you just talked about, yeah. What's the
method I
difference
talked-
between Thompson sampling?
The one on the slides had no Bayesian feel to it at all. So, but Thompson sampling is exactly what I'm talking about. But
Thank
you
you.
can also use Thompson sampling or variants of Thompson sampling with a more full RL. There's really interesting work in the RL community going in that direction. And a lot of it uses a bootstrap approximation to an approximate posterior.
Thank you very much.
Yeah.
Thank you. Any other questions? We're going to take a last question. Okay.
Yes, let me ask you a very biased statistical question then. To what extent do you feel that this study will be representative of real life? Because people in this study are continuously reminded that they're kind of part of a scientific study, right? So they may behave different than in real life.
Right. So this is really important point. Okay, so so this is there's several studies in a row. We're funded to have multiple studies. And so a big issue that it's often ignored, this is a useful thing if you're a theoretician to realize that in these kind of studies, in some of these studies, if you're not careful, the health scientists will have a protocol in which they contact the users if their sensors, for example, if their toothbrush is not charged, or if they're not answering questions on the app. That's all part of the treatment. You have to think of it as part of the treatment. Now, in this particular study, it's the first one, and there we have the protocol. We do have a protocol for contacting the user, and we're going to have to view that as one of the intervention components. When we go on to the next set, we're going to end up we're going to have a comparison. It's going to be a randomized control trial where one is the algorithm, one side's the algorithm, and the other side is the app, but without the algorithm. And there we won't be able to have the staff call individuals. The critical thing in this type of domain, the health science domain, is whether or not the protocol, any contact with the user is protocolized. That's the critical thing. And then that has to be stated up front when they write about the work in a health science venue, because that is part of the intervention. Yeah, I'm totally with you. This is a big concern.
Okay, thank you, Susan. Let's give Susan a big applause. I will make one important announcement. Actually, last night, Regina doesn't allow me to announce, but today we're going to announce for our next year ICSDS conference, and the location will be. Are we, Mikali? Mikali, are you going to show us the location? Are we going to? Okay, just hold a second. You can make a guess. What do you think? You already know the solution. Susan, you already know the solution. You may forgot after your plenary talk. It's in Europe. Hint, Europe. Okay. December 18, 21st, 2023. And that will be CCB conference site. We still didn't know the location yet. No, yet. Okay. Mikali, can you go to, voila, okay, Lisbon. Portugal, Lisbon. And I also like to introduce our next year local committee, the group of wonderful ladies, okay? All the lady teams are really good. Would you like to come up? Yavita and Teresa, Eunice, Maria, okay? Come up. You want to give a little bit? Okay.
Good morning or good afternoon, good morning. You are all welcome to Lisbon, and I hope that the weather is not similar to the weather we have had this week and last week with a lot of floods. Let's hope that in 2023 we have better weather. At my age, I shall have only a marginal role in the organization of the event. Indeed, when Regina, I do not know where she is, she's there, sent me an email about the 2023 meeting in Lisbon, I was a bit frightened and I thought, okay, maybe not myself, but I contacted the research director of my center, and we together found a group of people, and they are very enthusiastic young people who are enthusiastic about the organization of the ICSDS conference in 2023 in Lisbon. Okay, so maybe you want to say some words? I do not know.
Hello, my name is Teresa. I'm really very happy that we are organizing next year the ICSDS. It will be a great pleasure to receive you all, and I want to thank deeply to Regina and Henny for the invitation and for remembering and recalling that Yvette chaired a very important meeting of ISI in 2007, which was a very huge success, and people enjoyed very much to visit Lisbon. So I think that we will do our best to receive you in Lisbon and to make you feel the city, the gastronomy also, the monuments that we have around CCD that are very nice. And the weather, we hope that it will be fine. We will call St. Peter and order it in advance. So not to send rain and to send good weather. So I hope you all get enthusiasm to visit Lisbon or for the first time or revisit it if you have been there already. So thank you so much for all your attention.
Hi to you all. My name is Eunice, and I'm very enthusiastic about this opportunity to welcome this conference in Lisbon. It's a great place to be, and thanks again for the opportunity for Professor Yvette to remember me and all my colleagues at the Faculty of Science in Lisbon. And I hope to see you, all of you, next year by this time, and to borrow all your presents for Christmas in that time of the year in Lisbon. Okay, so thank you all.